Hello everyone, welcome to 10-Minute Physiology. In today's video, we're going to be talking about how capillary pressure works in under 10 minutes. So with that, let's give it a go. So I would like to start off by first looking at Ohm's law of hemodynamics. Now, Ohm's law of hemodynamics basically states that the pressure difference between 2 points is equal to the flow times the resistance. And the main thing that I want you to gather is that as we increase the resistance, we increase the pressure difference between 2 points. Now, to further hone in this concept, let's look at an example. So in this example, we have a blood vessel, and the vessel has two openings, opening 1 and opening 2. Now, opening 1 has a pressure of around 10 units, and opening 2 has a pressure of around 4 units. And as we know, fluid is going to flow from the area of high pressure to low pressure. So therefore, the fluid would flow from the side with 10 units of pressure to the side with 4 units of pressure. Now, the pressure difference in this case is equal to 6 units, because 10 minus 4 equals 6. How would the pressure difference change if we were to increase the resistance between the 2 points? Well, one way we can do this is if we were to add a plaque inside the vessel. So by adding a plaque inside the vessel, we are decreasing the radius and therefore increasing the resistance. So how would this increased resistance affect the pressure difference? Well, the pressure at opening 1 would be unaffected. It would be still 10 units of pressure. But what would be the pressure at opening 2? Well, in order to understand that, let's bring out our equation again. So Ohm's law of hemodynamics states that the difference in pressure is equal to the flow times the resistance. And as we increase the resistance, we increase the difference in pressure between 2 points. Now, in the stenotic vessel, which is right here, what happens is that the stenotic vessel has a smaller radius than the normal vessel. So therefore it has a higher resistance. So what we would expect is that the pressure at side 2 in the stenotic vessel would be less than the pressure at side 2 in the normal vessel. So maybe we would get a pressure of around 1 unit at side 2. Now, to further hone in this point of resistance increasing the difference of pressure, we can calculate the difference in pressure for each of these vessels. So the difference in pressure for the normal vessel is 6 units, and the difference in pressure for the stenotic vessel is 9 units. So the main thing that you have to take note of is that as we increase the resistance, we increase the difference in pressure between 2 points. So now what we're going to do is we're going to look at the diagram that we're going to be using for the rest of the video. So this is the diagram we're going to be using, and each of these bars represents a different vessel. And these vessels are all connected to each other, as you can see. So the red bar is the arterial, the pink bar is the capillary, and the blue bar is the venule. Now, each of these vessels is going to have a different pressure. So the average arterial pressure in this case is going to be 60 torr. The capillary pressure in this case, we're going to start out with 25 torr. And the venule pressure is going to be 15 torr. So what we're going to do with the rest of the video is we're going to see how we can change this capillary vessel, and we can do it in many ways. So we're going to be looking at 4 scenarios, and we're going to see how these scenarios affect the capillary pressure. So scenario number 1. So the first scenario is when we dilate the arterial. So when we dilate the arterial, what is going to happen to the capillary pressure? Well, the main thing that we have to answer is we have to bring in our Ohm's law of hemodynamics again. So remember that Ohm's law of hemodynamics states that the difference in pressure between 2 points is equal to the flow times the resistance. And as we increase the resistance, we increase the difference in pressure. Now, in this case, what's going to happen is that the resistance is decreased in the arterial. And this is because we have dilated the vessel, so therefore the radius is increased. So how is this going to affect the capillary pressure? Well, how it's going to affect the capillary pressure has to do with how much fluid is entering into the capillary. So whenever you dilate a vessel, you have more blood flow going into that vessel, because blood flow is actually like electrical current. It likes going down the path of least resistance. So the lower the resistance, the greater the amount of flow entering into that vessel. So in this case, if you were to dilate the arterial, more flow would enter into the capillary, and whenever you have more fluid flowing into something, you increase the pressure of that thing. So If you were to dilate the arteriole, the capillary pressure would increase because you have more fluid flowing into the capillary, which then exerts a pressure on the capillary wall. Scenario number 2. So scenario number 2 is the opposite of scenario number 1, and in this case we are constricting the arteriole. So what is the capillary pressure now? So what we would have to bring up again is our Ohm's law of hemodynamics, and the main thing to remember is that as we increase the resistance, we increase the difference in pressure between 2 points. Now in this case, we increase the resistance of the arteriole, and the reason why is because we decreased the radius. So how is this going to affect the capillary pressure? Well, it has to do with flow again. So remember that blood flow likes to go down the path of least resistance. So if you increase the resistance, you decrease the blood flow. And what we see here is that in this case, if you were to constrict the arteriole, less fluid flows into the capillary. And whenever you have less fluid flowing into the capillary pressure will decrease, as you see right here. So when an arteriole constricts, the capillary pressure will decrease. So scenario number 3. So now we're on the venule side and we're manipulating the venule. Now in this case, we're going to dilate the venule. So how is this going to affect the capillary pressure? Now the main thing to remember is Ohm's law of hemodynamics once again, and in this case what we're doing is we're decreasing the resistance of the venule. So we decrease the resistance of the venule by dilating it and by increasing its radius. So how is the dilation of a venule going to affect the capillary pressure? Well, in this case, we have to consider the fluid going out of the vessel. So whenever you dilate the venule, more fluid flows out of the capillary. So whenever you have more fluid flowing out of the capillary, this will decrease the pressure. So the pressure will go from 25 torr to maybe around 20. So the main thing to note is that when the venule dilates, the capillary pressure decreases. So in the last scenario, we are constricting the venule. So how is this going to affect the capillary pressure? Well, once again, we're increasing the resistance of the venule, and we're increasing the resistance by decreasing the radius. So to answer the question of how this is going to affect the capillary pressure, we have to look at fluid flow. So when you constrict the venule, you'll cause less fluid to flow into the venule. And when you cause less fluid flowing out of the capillary into the venule, this will cause more fluid to stay within the capillary, which will therefore cause the pressure to increase. So when the venule constricts, the capillary pressure increases. So how do you calculate the capillary pressure? Well, the capillary pressure is going to be calculated by actually a very difficult equation to remember. And this is the equation that you can use to calculate it, and I'm going to talk about what each of these values are. So the first value, R post, is the resistance of the venule. The second value, R pre, is the resistance of the arteriole. PA is the pressure of the arteriole. And PV is the pressure of the venule. So you can use this equation in order to calculate the capillary pressure. So why is the capillary pressure so important? Why did we spend all this time talking about it? Well, in order to understand that, let's bring up an example. So this is your vessel, and in this vessel, we have a certain pressure. Now let's just say that we have a pressure of around 10 units. Now the pressure inside this vessel is going to cause fluid to move out of the vessel, and the movement of fluid out of the vessel is called filtration. So when we have a certain pressure, we have a certain amount of filtration occurring. So what if we were to increase the pressure? So if we were to increase the pressure inside the capillary to maybe around 30 units, what would happen is that we increase the hydrostatic pressure inside the capillary, which would therefore cause more fluid to filter out of the capillary into the interstitium. So the reason why capillary pressure is so important is because capillary pressure determines fluid balance. So the higher the capillary pressure, the more fluid is filtered out of the capillary, and when you're talking about fluid flowing out of capillaries and into the interstitium, this becomes important for certain conditions like edema or swelling. So this is why capillary pressure is such an important concept to understand. So in summary, we talked about the Ohm's law of hemodynamics. We stated that the higher the resistance, the greater the difference in pressure between 2 points. We also talked about when the capillary pressure increases, and we saw that the capillary pressure increases when the arterial dilates and or when the venule constricts. And we said that when the capillary pressure will decrease when the arterial constricts and or the venule dilates. And lastly, we talked about that the higher the capillary pressure, the greater the amount of filtration. So I hope this video helped you understand capillary pressure and how it is generated and how it can vary. And I hope to see you in the next one. So good luck in your studies and see you next time.